coming, like very few basic questions. If you learn this, whatever this radar software, whatever algorithms that we are going to talk, are you going to pursue a software kind of jobs in industries, or hardware kind of jobs in industries, with whatever today's content that is being planned and the orientation that is given? What do you understand? Do you feel it is a kind of software job? Are you being prepared for a software job or not? It is still software job. No, I'm not connecting with the hardware. I'm actually trying to take out a basic wrong meaning that we generally attribute to the software. Software in our country, due to the nature of the what is called more quantum of the jobs that you see and what you hear from different high-tech city, different companies and all, a very basic opinion that struck to us, software means it is completely different, something like customizing some web app or banking this one and all. So that only we think as a software. So but software is everything, like you write for a radar, or you write for sonar, you write for this LCD projector, you write for a laptop, or you write this, everything is a software. Here, what I would like to emphasize, what kind of software developers are usually not seen as the software developers, I'll tell you. See, any software development has got a concept, of domain or the application level knowledge. Okay. So see, for example, you are working in any software company that you work. If you are developing a software, if you are testing a software, there is an element of application-wise learning, which also can be called as a domain. Okay. If you are working for a banking company, then you will learn about different types of accounts in your bank, savings accounts, current accounts, fixed deposits, interest rates and all. These things you would not know as a basic C programmer or C++ programmer, as a Java programmer. So C, C++, Java, programming, Linux, operating system, these are technologies, software technologies. So with the knowledge of software technologies, when you join a company, depending upon the company domain or company application, you will learn application, then you build the product, the software product, or the software combined with the hardware as an embedded product, something like that. So any software engineer, without learning the application, intricacies and giving value addition application wise also, not only domain wise, cannot grow in the career. But eventually this is not taught at colleges, because anyhow which company you join, which application you are going to work, that is not known. However, the applications which are related to the core subjects of electronics, something like signal processing, radar signal processing, that today what we are going to emphasize and you will do in industry, it is not that easy that you just learn this application from your seniors or just by reading the manual or something like that. But if it is a banking application, or if it is a what is called some insurance company website development application, or if it is customizing some ERP package for some car, what is that application, these are something like the knowledge is there only. You will learn from that. There will be a formal course for a week or two, you will learn. But when it comes to the applications which assume that you have some signal processing background, that's why mostly, let's say, an IT guy is not more suitable when you compare with the electronics, especially MTech electronics signal processing guy is more suitable for a radar software developer. You understand? So understand, these are also software domains. All the things that you see as an advantages of software. What is the advantage of a software that people talk about? No, simulation is okay, but in general, you get more packages, right? You get more packages, you get chance of work from home, or you know something like if your skills are very high, your career growth can be damn faster, isn't it? In software, all that dynamism is possible, because software is all, if you know how to use an existing already internet available library, maybe somebody takes a month to develop, you can develop in a day also. So software is such a what is that called, wide dynamic area. It is purely left to your imagination skills or your IQ skills or your core competencies. Of course, I don't say that in hardware that is not but definitely when you compare with the software, in hardware, you have invariably some amount of what is that called, association with the physical things that happen, right? Like for example, you want to solder a PCB, whether you like it or not, it takes actually 1 hour. Okay. You want to send one PCB, some 14-layer PCB for manufacturing, it takes 15 days. And unlike that, in software, lot of things are virtual. Lot of things are, what is that called, models in your computers, where the computer runs at 2 gigahertz clock. Things are fast. It is only left to your imagination. So I strongly encourage people, the people sitting over here, the people who are online participants, and the other whatever people, if you think you have actually good software coding skills and all, do consider adding to that software your core electronics related application knowledge. You become actually more valuable entity in the industry. You understand the point? Yes. Is it a very niche industry like radar signal processing and this one? Definitely yes. When you compare with website development kind of thing, because everybody needs website. Okay. When you talk about, let's say, sir, I learn a Java package for building a website. Is it that more popular or something? The radars, obviously that is more popular, maybe 100 times more popular. At the same time, anybody can actually become a competitor for your job. Are you getting? If a recession comes and all, but having your core electronics or core, signal processing, additional application knowledge, and working for radar or ultrasonic, I'm going to talk about radar is a very broad subject. In fact, with the increased what is it called, utilization of the radar in the automotive industry, in the unmanned aerial systems, drone industry, it has become much wider. So when you have the knowledge of this application, your chances of hiring is more, and your career is more stable, sustained. If it is also aligned with your personal interest, then you can rock in the career. What do you mean by personal interest? It's, of course, probably you are here, it is not a mandatory thing, right? No college, your college has not forced, your HOD is not forced, or our organizers are not forced you. You came here with your interest. It means you have some zeal, interest on the signal processing. If that interest is with you and you have a proper approach towards learning the subject, you become more and more valuable to the industry. You're getting the point. So this is what. So understand all the benefits of working in the software industry will be there when you work in embedded software also, will be there in the, what is that called, radar kind of applications also. With the increased application of a radar, India needs more and more radar kind of working companies and more software and hardware engineers who work on the radar technologies. But this event is focused towards basically software. Okay. So let's get into this quickly. So you guys understand why we are doing this. We want to encourage you, take the software category profession, apply your signal processing knowledge, learn from existing algorithms, and build the products specific to each application. For example, here, the engineers who work, maybe we have around 10 engineers, group of engineers in software, they work on radars. They do research on the drone detection, because our products are drone detection radars. Okay, something like that. So we do more deeper research into that and customize the algorithms. But basics are important. And unfortunately, already existing Indian industries, they are not in a position to sustain a very good training programs right from the basics. One thing, it costs, and in industry things people want faster. And if you have already some prerequisite knowledge and skill, yes, you are definitely distinguishing yourself than your other competing students. So your chances of hiring becomes good, more. Okay. Yeah. So we'll just talk about broad applications. That's only just to give you a picture that what we are learning. Yes, maybe after first half an hour, we'll go deeper into electromagnetics, radar, pulse Doppler, automotive radar, but they are very broad. The basics are even can be applied in a very broad areas. We will talk more about the FFTs, signal, time signal properties, but since you are most are undergraduate students, I'll start from no background assumption. Okay. Then pulse Doppler radars. So this is the radar that what we built. Today you are going to do lab sessions on its software models, and you're also going to see the live demo of the radar. Okay. I don't know whether live is planned, recorded is planned. When you go to the lunch area on the top floor, you will be able to see physically this. But depending upon whether today there is a sortie or not, they'll show either a live or actually a recorded demo. Then we will talk about FMCW. Our industry is not FMCW. but we want to cover because as a growth areas, you have two industries parallelly growing. Okay, one is pulse Doppler radar, which is mostly military wise used and all. FMCW, which is automotive companies and all this. And let me tell you, in Indian automotive companies, okay, automobile companies and all, there are not these divisions. Okay, as and now we are importing those technologies, importing from different companies, global companies. But obviously, any import comes with a huge cost. Okay, we can't beat the world market. So there is a necessity for people work on automotive radars and sustain the Indian automobile industry, going to the next generation of driver assistance systems. What is it called? Automatic, self-driving cars. All these features. Okay, let's get into. Okay, can you go to next? Very a simple animation. I just picked from the URL which is given at the bottom. So radar is very simple. Very simple. You emit electromagnetic energy, and if there is some object, there is a reflection that comes, and you process what you emitted and what reflection came by some signal processing techniques, by which you get to know the the target distance and the target velocity. Now let me make your imagination even more and more broader and more general. In a way, your eyes also is actually working like a radar only. Sir, morning. I'm not seeing you. Yeah. So our visual system also working as a radar only. Sun is a source. Sun or your artificial light sources are the transmitters. And the light waves also electromagnetic waves, right? They are going and reflecting onto the different objects. And your eyes are acting as a receiver, radar receiver. Now you may understand, sir, where is the synchronization between the transmitter and receiver? This is the synchronization which is built automatically in our gene system. So it is an understood, what is that called, characteristics. Like, each colors has got a different wavelengths and all. Like since his t-shirt is absorbing all the colors and only reflecting, only not observing and rather reflecting the red color frequencies, I'm seeing red color. So there is a kind of algorithm which is built in our genetic system. So it is an example of a bistatic radar. Bistatic radar is something which you don't understand, don't worry. The transmitter receivers are separated. Transmitter is at one place, receiver is at one place. It is called a bistatic radar. Monostatic radar is a transmitter, receivers are co-located. They're at same place. Okay. Whatever demo that you are going to see is a monostatic. Both are at the same place. Okay. There are two separate antennas there. It's okay. But they're the same circuitry. They're at the same place. Okay. Now, this is like example bistatic radar. You see now, so radar is everywhere. Okay. Now, you know that the bats, they emit frequencies around 1 lakh hertz and all, and they also do the reconnaissance, okay, finding their targets or maybe other things through completely with only the reflections that they come. And the sonar, which is underwater, you must have studied in your school days the subject sonar, which is using acoustics underwater, getting the echo, that is also a radar. Only thing is, in our today's session, we will not be diverting into all those because each of this area has got its own this one. Like, you must have heard about LIDAR, okay, laser based. Because when the wavelength changes, when the frequencies change, the phenomena of the wave, the scattering phenomena, the reflection phenomena, all these change. So processing techniques differ, but the principles still remain same. Like the basic principles of fast Fourier transform, all those remain same. Now coming to a basic radar, just emits a signal, you get a reflected wave, then you get to know the distance. Okay, can you go to next? Now, how this works? Now we are going into the electromagnetic radars. That is nothing but general radars. They travel at speed 3 × 10⁸ meters per second. Okay, I have a quick question. Let me see who can answer this. A 9 GHz signal, okay, which is called X-band signal, or maybe some 74 GHz signal, which is an automotive radar. Will both of them travel with the same speed, 3 × 10⁸ meters per second? Yes. Okay. Please understand, your physics is actually physics is mother of all engineering subjects. Huh? So it's very important, if you are keen on building your career in the core product development, you should give some time and go back read your 8th, 9th, 10th physics also once. It's very easy, right? And today you have a lot of online video lectures and online things and all. So those things are very, very important. So any electromagnetic signal, okay, they travel with only 3 × 10⁸ meters per second velocity. So whatever we are discussing about these basics, they are applicable to all the segment of radars: L-band radar, X-band radar, 74 GHz radar, and all. For 1 microsecond, the signal travels 300 meters. Simply multiply the velocity with 1 microsecond. If you have a target at 150 meter, then its delay will be 1 microsecond. So I send a pulse. The target is at 150 meter. I send a pulse. So what happens? The signal will go 150 meter up, 150 meter down. So when I try to compare the difference between the pulse when I emitted and the echo pulse when I received, it will be 1 microsecond. So in radar, it's a thumb rule that is followed. 1 microsecond delay between the transmit receive is equal to 150 meter. So tell me, if it is 10 microsecond, how much will be the target range? If I notice the transmit and receive pulses are differed by 10 microseconds gap, how much is the range? Sorry, 1.5 kilometer. 150 meter into 10, so it is 1500 meter, 1.5 kilometer. Okay, see, in a system, in your environment that you are measuring, you will have multiple targets. Okay, so when you have multiple targets, you get multiple echoes. That's where the challenge comes. If it had been the environment is only one target, assume you are in space, isn't it? You are in space, and you can assume that for lakhs of miles, there is no other object. The very simplest radar algorithm also may work. But in our natural environment, whether it is automotive or military applications, you will invariably have multiple targets, and you want to build capability of detecting multiple targets. Okay, and at the same time, the more challenging comes is, in addition to targets, there is an annoying background will be there, isn't it? A disturbing background will be there, which we call as a clutter in radar. So to handle this clutter, to handle this multiple target detection, we get into the signal processing algorithms of radar. Otherwise, a simple time delay measurement would be enough, isn't it? Just I send a pulse, receive a pulse, I measure the time difference, I'm able to tell. That's as simple. But it needs to be more complicated than this, because in a real scenario, you have multiple objects, and there is clutter, which is unwanted background, which will always be there. Can you go next? This is a very interesting thing. I keep asking people, Doppler. What is this Doppler? I picked up this animation from the URL that is given here. To understand Doppler is taught in our school days. Okay, I believe in 8th standard and 9th standard, you have Doppler. It's not very complicated. It's very easy to understand the Doppler. Now, if you see this animation, what is being shown, the source which is emitting the signal, okay, is traveling that direction. There is an observer which is labeled as a front observer. There is an observer labeled as a back observer. So if the particular source that is emitting, it is actually emitting a circle only. If you see, the source is not in the center of the circle. Source looks to be on the drifted direction of the circle. The reason is, see, look at me. So this is the direction in which the signal is going, and I am also moving. Okay, the source is also moving. So what happens? Whatever these things, very important term, what is called wave front. Okay, which is nothing but phase. All phases are wave front is nothing but the plane in which the phase is same for all this one. So phase is very simple to understand. In a sine wave, you can simply call 0 degrees one phase, 90 is one phase, and all like that. Okay, so what is happening now? Obviously, whatever the lines that are being shown, they are with some phase shift. Let's say, for example, 0 degree phase shift we took as a reference. So now, when you are moving that direction, one is because the distance is getting reduced, you are receiving it faster, isn't it? Let's take a simple example. This animation, which is taken from this URL, is about the acoustics. Principle is same. I mean, like for our normal sound, okay, sound waves which travel with 330 meters per second, it is taken from in that context. So 330 meters per second. What does it mean? It's a simple thumb rule. If you want to calculate, right? Once you know the frequency, once you know the velocity, you can calculate the wavelength, isn't it? Wavelength is equal to velocity divided by the frequency. Okay, so now velocity is 330 meters per second. Now let's take for our calculation convenience, the frequency is 330 hertz. Okay, now you can calculate the wavelength, the distance. See, it is actually like, if you see a particular sine wave, there are two ways to visualize a sine wave. There are two important ways to visualize sine wave. Can you just stop the screen for a while, screen sharing for a while? This is a very, very important visualization. Let me tell you, I see people who can conceptually apply logic in reading papers, in reading articles, in understanding, in debugging and all. They will have one distinguishing characteristic from the others, that they visualize. They can actually visualize the phenomena. So visualization is very important in for an engineer, and it is more important in software engineering, because a lot of things are abstract. They are not visible in front of you. At least in hardware, they can see there is an op-amp, there is an oscilloscope, there is this one cable length, wire and all. But in software, everything is abstract. We talk interface, we talk FFT, time domain, characteristics, power, amplitude. Everything is actually imaginary, abstract. So you should be able to visualize. Now, so that's why I would like to spend some time on this. So this is a basic, very popular, our total engineering is around this only. Could it be electronics, mechanical, any of this engineering? They all based on only this particular signal. Okay. Now, there are two important characteristics of this. One is like time period. We talk about the time period. If the time period is 1 millisecond, then you say its frequency is 1 kilohertz. Second, you talk about the wavelength. Okay, wavelength is different. So when you want to calculate the wavelength, so you take velocity. Of course, for electromagnetic waves, we use that C as a symbol, 3 × 10⁸ divided by the frequency. So I will tell you something by which you can usually visualize these things. Now, I want to go to the physics basics, which is taught right in 7th class, and explain. You studied about two types of waves, right? What are the two types? Longitudinal, isn't it? Transverse, you studied about two. So in like our sound waves are what type of waves? Whatever we are communicating, longitudinal, right? So the particles move, and the wave energy also moves like this. The particles move like this, wave also moves like this. You got it? Whereas our electromagnetic signals are, they're not longitudinal, right? If the wave is moving like this, the particle characteristics, the practical properties in our acoustics, it is a mechanical things are easy for us to visualize. That's why in your school days, first sound is taught before light and other things. Mechanical easy. If I throw Vishnu, he'll fall down, isn't it? I can visualize that. Shall I just push him and try? So it is very easy to visualize. So our particles are also vibrating like this. The energy is connecting, isn't it? So I speak, the particle here couples the energy to next particle, next particle, next particle. Achha, how about I'm saying particles are carrying this energy? If there is no air here, can you hear me what I speak? If there is no air here, absolutely there is no air here. There is no medium, nothing. If I speak, can you hear? You can't hear. You can't. You have air here. Air is with a lot of molecules, that there's oxygen, all these molecules. So whatever is present, those molecules, I'm pushing them. I'm just pushing forward like this. So I'm creating this disturbance, right? So this is actually getting coupled to particle and going like this. In electromagnetic waves requires air? No. How it works? If there is no air, how? See, because air is there, I am able to push like this couple of particles, and they are carry forwarding their energy and all. How the electromagnetic, if nothing is there, what will move? How electromagnetic wave is moving forward? Isn't it? Because see, all your particles, if I push Vishnu, he'll be pushing her, and it will be going like that. It's easy to visualize. But electromagnetic, how it is going? It is definitely going. Otherwise, sunlight would not reach us, isn't it? All these radars won't work, nothing. How it is going? See, electromagnetic wave is electric energy creates a magnetic energy. Magnetic field creates electric field. You're getting the point. That's what you see. You saw the very popular electric magnetic fields 90 degrees to each other and the wave moving, right? So spend on it. Okay. Do meditation on that, seeing that. Okay. If you want to be core electronics engineer. See, it's a very, very interesting phenomena. Go back to your electromagnetics first course. You studied about the Ampere's law. You studied about the Maxwell's equations and all. Don't get into the math and don't worry, but just try to understand an electric field can create a magnetic field, and a magnetic thing can create an electric thing. That much easy to understand. So, if the wave is going like this, if the electric field is like this, that creates a magnetic field like this, and that creates, I mean, don't take my example very seriously. It has to be like that right hand rule that and you studied in your waveguides, the transverse electromagnetic and inside a cable transverse, all this you studied, right? Just be very vague picture, but try to understand that the electric field like this is creating the magnetic field like this, and this magnetic field is creating electric field like this. See, one field creating next. That is how that goes, the energy goes. Now come back to the subject, trying to understand what is this phase, what is this time frequency, and what is a wavelength. Okay, now assume that you have got a camera, like something like a camera, and that camera is a fictitious camera. It's like God created with infinite capabilities. What is the capability of the camera is it can shoot at a very, very low resolution, maybe picoseconds and femtoseconds, attoseconds, that low level it can shoot. What it can shoot? It can shoot the phase of the all these electric fields that is creating at one instant of time. Okay, so if that is taking a photograph, and that photograph, when you see, what you observe is here, whatever is the particle which electric field that is present, it is at 0 degree phase. Okay, next whatever is present, it is with some 10 degree, 20, 30, 90. And remember, this physical height that I am showing also as an illustration purpose, because we people to visualize, we only visualize this time, okay, which is passing, space which we can feel, that only visualize. But actually there is nothing growing here. It is the electric field, electric charge, okay, something like that. If there is a current that is there in the socket, 230 volts means something grow, then nothing will grow. So you have to understand the illustrations that are shown in your books. What is actual reality? Okay. So the way how socket inside, whether it is 10 volts or 230 volts or 2.2 kilovolts, it will look like that only. Same way, even though we show for illustrations that something is amplitude is increasing, it is only for the easy for understanding. Okay. Now, imagine this is a particular signal whose frequency is 300 megahertz. If you substitute 300 megahertz into 3 into 10 to the power of 8, you get lambda is equal to 1 meter. What it means is, when you shoot with that camera, if you observe, you see that these all fellows which has got face like this, and after exactly 1 meter, the electric phase that is present here, after 1 meter will be same. Got it? There will be 0. Again, the one which is at 90 degree here, and after 1 meter will be 90 degree phase. You understand? This is what the wavelength. Wavelength is at a given instant of time. Okay. What is the spatial, variation of the phase of the electric at a given instant of time? You understand? It is very, very fast. This is very important principle. The people who understand and who visualize the wavelength like this, they can understand the beamforming algorithms very easy. Otherwise, beamforming looks very complicated. Okay, because in beamforming, I think for most of you, beamforming is completely a new term. Is my understanding correct? Is a new term, or you ever heard? Or let me put in your known terms. See, good thing is all your subjects are so well framed that they cover all basics. Maybe terminology may not be covered, terminology in industry may be different, but the subjects are so well written, the syllabus is so well written, they cover all basics. In your antennas, you study this linear array. Remember, that is only beamforming. In the linear array, something has been shown, their signal is coming from this direction. This element is receiving first. This element is receiving with some phase shift. They also show the calculation of the phase shift. They say the extra distance that is traveled, something like that. Beamforming is nothing but a multi-antenna system where each antenna is having a different characteristics, but together with multiple antennas, I create a beam of my desired purpose. maybe I can create beam here, beam here, beam here. They call beam forming. But the principle of beam forming is what you studied in your antennas as antenna arrays. You studied. No, but what I'm just trying to hint, wavelength is nothing but an instantaneous situation of your signal at a given instant of time. This one. Now, look at the different one now. Okay. What is this sine wave? The same sine wave when you draw and when you try to show, when you put the x-axis, when I show like this and this, I say 1 meter, I'm actually showing you at a given instant of time the spatial picture. Okay. Let us see another one. Sometimes we draw like this. What is the time period of this 300 megahertz signal? How do you calculate time period from frequency? 1 by f. How much it comes? 300 megahertz. 300 mega. So maybe it comes around 3.33 nanoseconds. Isn't it? 1 by 300, 3.333 nanoseconds, something like that it comes. Now let us try to understand what is this 3.333 nanoseconds. Okay. Now, you are here only. This is one particle. Come back to the previous example. Now this, if you have a watch, which is a very, very fast, okay, you can take readings at femtoseconds and all like that, you can observe that this particle going up in the sense, again, remember, it's only electric, increasing its of electric energy like that, okay, and coming down and again coming back to zero phase. That takes, the amount of time that it takes is 3.33 nanoseconds. Okay. If you can visualize a sine wave when x-axis is written as 3.33 nanoseconds, it is a time domain phase variation of a particle in space. Actually, it is not particle at a particular situation, at a particular position in your space. It's time-wise phase characteristics. Whereas when you draw this lambda as basically 1 meter, at a given instant of, now you're not letting the time to pass. At a given instant of time, you take a complete snapshot at the wider space, then you see that as this one. You understand? This is how you have to learn a sine wave and its properties. Then you will get to know how to play with these things. It's visualizing this as a time will let you to do all designs with your oscillators, phase noise, and these are all related to this. Whereas visualizing this with the lambda as 1 meter will let you to design antenna array systems, beamforming systems and all. You can put a presentation back. Yeah. So now it is very easy for you to understand. Now it becomes very easy for you to understand. What is happening when I am standing here only, there is no movement between the transmitter receiver. When there is no movement between transmitter receiver, it is very, let's say for example, my frequency, I will go back to the sound signal, which is, let's say its frequency is 300, how much I said? Yeah, let's say 300 hertz. Okay, 330 hertz. Then it will be 3 milliseconds, isn't it? 330. I took for my convenience some 330 hertz frequency. Okay, which is equal to basically what its time period is 3 milliseconds. So what might be happening? I'm here, no movement between the transmitter receiver. So the one complete phase shift, because I'm talking about sound wave, it is traveling like this. It takes 3 milliseconds reach there. Now because I'm moving. So it means these particular, I'm pushing little forward. So now it won't be 3 milliseconds, it will be lesser than 3 milliseconds. You understand? Because the time when it is becoming less, let's say 3 milliseconds has become 2.5 milliseconds. Obviously, I'm moving towards this. If it is 2.5 milliseconds, you back calculate the frequency, it comes basically 400 hertz. Now you see frequency is increased. I'm emitting 330. She is receiving basically, now 400 hertz. What happened? This is called Doppler shift. Okay. Whereas the person who is that side, you got it. It'll actually, what will happen, he is getting late. Okay. Now he will take more time to receive that because I'm moving like this, right? While I'm creating disturbance, I'm moving like this. So he needs more time. You got it. Probably it will result into 3 milliseconds may become 3.5 milliseconds. Something like that. Don't connect these two examples because when you connect these two, they need to be mathematically same. I can't have two different velocities, right? Just take as a separate examples. So that can become basically, something like 3.5 milliseconds or maybe 4 milliseconds. Then the frequency that he sees is 250 hertz, something like 250 hertz. You see this? This is the Doppler shift. Is it anything difficult to understand? But do you think, sir, this level of understanding is needed? Sir, I remember one equation, that is Doppler shift FD is equal to 2 VR by lambda. That equation I remember, I substitute and calculate. Is this remembering is enough? Not enough. Because it looks so simple, but when you start applying in a problem, you deal with hell lot of things. There is something called, Doppler, micro Doppler, and when a target, let's say, for example, you are building a radar for a, what is that called, drone or quadcopter. The drone, when it is moving, the drone is coming with some, but the drone blades are moving it much faster. That creates something called micro Doppler. So in any engineering, whatever you studied as a basics in physics in school days and associated mathematics and tools, techniques, subjects, signal problem you studied in engineering will further need to be applied in a much more complex manner in a practical application. So being able to visualize everything will help you to understand this in a scalable model. You will be able to easily understand this. Are you getting my point? Do you agree this point that when a drone is coming towards me, drone may be moving with 10 meters per second, but the blade that is rotating, okay, is moving with much faster. So the blade is like this. When the blade is rotating, maybe with some 1000 RPM, this tip of the blade is actually hitting much faster. My electromagnetic, it creates a different Doppler. Okay, so a deeper understanding and building an application with the deeper aspects of the deeper scientific aspects for a better versions of the product, better features of the product will require visualization of the subject concepts. Hope there is enough time we have spent on Doppler. Can you go to next? So it's very simple. A positive Doppler shift is created for an incoming target. Okay. And a negative shift is created for an outgoing target. Simple, the way how we achieve. And remember, does it matter who is moving? This is a very general question. You can apply your common sense and tell. Go to the same example, like receiver, transmitter. Does it matter who is moving? Like let's say one case stationary, I'm moving with 1 meter per second. Case 2, I am stationary, she is moving with 1 meter per second. Does it matter? It doesn't matter. Okay, it doesn't matter, right? Acha. Let's say there are 4 cases. Case 1, none of us are moving. Case 2, I am moving with 1 meter per second. Case 3, she is moving with 1 meter per second. Case 4, both of us are moving with 1 meter per second. So tell me, 2, 3, 4, all of them are same? Which are same? 2 and 3 are same. I am moving, she is stationary with 1 meter per second, isn't it? I am stationary, she is moving with 1 meter per second. Both. What about the 4th? Is it not the same? We are also good, equal. 1 meter, 1 meter. Huh? Will it be same? Who says it's the same? Please raise your hands. Okay. Who says it is not the same? Please raise your hands. No, both are coming towards. Yes, she is coming 1 meter per second. I am also coming 1 meter per second. Then, so will the Doppler increase? With case 2 and 3, will the Doppler increase when both are moving towards 1 meter per second? Yes, it will increase. It will increase. So what matters is finally the relative frequency. Okay. Now you see the case 1, relative frequency is relative movement is 0. There is no movement. Case 2, 1 meter per second. Case 3 is also 1 meter per second towards. Case 4, 1 meter per second, 1 meter, effectively it becomes 2 meter per second. And the frequency will be double, the Doppler shift will be double than 1 meter per second. You got it? Case 5, I am also moving like this. She is going away 1 meter per second. What will happen? Nothing. It will be equal to the 0 Doppler. You understood this? This is what. These are very, very important principles in radar. How a Doppler gets created, positive Doppler, negative Doppler and all. And there are some special radars which are built exploiting these properties, that when I go very fast, I get some advantage in terms of getting a better detections because Doppler sense. They are called synthetic aperture radars. The radars, synthetic aperture radars, they create something different because of going very fast. Their capability of see, radar is also like a camera, right? It takes a photograph. I want to also, if you have given a chance, I want to build a radar which can give a very, very finer details of the environment. But it becomes very challenging. So I'm okay with, okay, you tell me whether target is coming here 2 degree or 5 degree, that much is enough. That's why we make a very simple one. But synthetic aperture radar would like to use this principle of creating the Doppler when you are in a movement for the benefit of getting a better detection of the image. Okay, if you're interested, please Google and read. Okay, can you go next? Let's quickly dwell on application categories. We just had a basic understanding, radar signals and all. So what we are going to talk today is about the electromagnetic wave based radar using sound waves underwater. The submarines, oceans, they do sonar. That is also same radar, only thing they're sound waves. Okay, acoustic signals inside the water. Then laser ranging, you must have heard of this, no? So using laser is also electromagnetic, but on the higher side of the frequency. Okay, closer to your visible light frequency, that is ultrasonic. This is very interesting. You get a lot of kits in the electronic sites and all. You can buy an ultrasonic sensor which has got a simple ADC and do all radar processing, and that's really fantastic. Somebody want to master the radar, you don't have to have a crore of radar, whatever that we build. You don't need to have. Just have an ultrasonic transmitter, ultrasonic receiver. What you need is ultrasonic transmitter should be driven by DAC from your microcontroller, microprocessor. Ultrasonic receiver streaming samples with an ADC should come inside your microcontroller. All the things of radar you can learn into. Okay, whatever we are studying today and everything you can actually learn over there. Okay, and good thing with this ultrasonic and this one is you can easily create a disturbance also. You can put a fan, normal table fan, which rotates like this, creates a disturbance. This disturbance you can detect in your signal processing on the received signal. Ultrasonic. But ultrasonic radars, I'm not just telling for the learning, they are used widely in the industry. Okay, can you go next? I have not much emphasized on application because that's easy to learn. You'll get from web. I just picked up certain things, and we are more onto the military side. I wanted you to learn, if you are interested on military radars, what DRDO builds, what Bharat Electronics builds, what private industry builds and all. Some YouTube link is given. But in military, in fact, who invented the radar? In which application radar was invented? Who? I don't remember. Okay, you can browse and get. It is for military only. See, most of the inventions would actually be driven by military, isn't it? You know that wireless communication, all these are mostly, of course, in the recent past last 2 decades, it is a mobile industry inventing a lot of algorithms, because the civil utilization of the mobile has has seen a bigger research interest. But before 1980s, you see most of the inventions are defense driven. In fact, your language VHDL has come in the DARPA research, okay, which is a DRDO kind of organization for United States. So most of the radar is also invented, okay, in this military context only. They want to detect incoming aircraft 200 kilometers away, 300 kilometers away, so that they can put their gun towards it and keep it ready, to fire. Now, yeah, military applications are enormous. Self-driving cars, that's a technology which is picking up last decade, and that's going to come, and it will do a lot of automation in terms of car driving, navigation, automatic cars. And these cars, instead of going on ground, they're talking about the going on air, flying cars, which is called unmanned urban mobility. Okay, you sit inside the car and just program, it goes. Okay, a big drone which is capable of your 70 kg, you will buy 100 kg capacity, so you'll just sit inside that, you'll go on that. But these fellows should not collide with each other and all, right? So management system, they all require radars. Okay, and self-driving cars, already that the companies who are doing research on automotive radars. Then radars for civil aviation. Yes, all your aircraft landing guidance, they're all connected with radar. If radars are down, if you have seen that rotating radar, at our Shamshabad airport, you must have seen that is rotating, secondary surveillance radar, primary radar. They're required. Civil aviation, industrial sensing, distance measurement. A lot of industrial sensing, distance measurement goes with these ultrasonic radars. In industrial automation, you might see some robot picks this object and keeps it here, and exactly it positions with some spacing of 1 centimeter. How it knows 1 centimeter is all with the ultrasonic ranging. Then weather radars. How do you predict something? Clouds are coming with so on so speed. So weather radars. Same principle is same, because that cloud is also acts like a reflector. Cloud with the charges. That cloud has a charge. That's so the lightning and all happens, right? So because it's having charges, it possesses certain properties of a metal. If this, you studied the basics of this electromagnetic course in the boundary conditions. You're all in the final year, guys, right? You did some course in electromagnetics, right? You studied the boundary conditions when electromagnetic signal is actually hitting a boundary. Depending upon its characteristics of that, certain energy gets reflected and all. You studied that if it is a metal, most of the energy reflected back. So clouds also, because they possess this static electricity and the electricity, this one, so they reflect. Certain frequency band is good for that. So weather radars are detained in this one. And that's the interesting thing. When you study the different type of radars in electromagnetic, the choice of the frequency will be more specific to the application. Okay. When you want to detect a long range, like 1,000 kilometers detection of an aircraft, you may choose some L band or S band, something like that. When you want very precise tracking for gun control and all, you will go to Ku band or Ka band, order of 20 gigahertz, 25 gigahertz, like that. Because as a wavelength reduces, your preciseness in measurement improves. Okay, your wavelength, as a wavelength reduces, your preciseness actually improves. That's why our eyes are processing very less wavelength, isn't it? Our whether wavelength of light will be smaller, wavelength of 9 gigahertz signal will be smaller. Wavelength of light is going to be smaller, because you know that electromagnetic spectrum, these signals, L band, S band, X band, after W band and all, these all light rays and all come. Because the wavelength of light is very small, okay, you are able to see very fine details with your eye. I'm able to see you are wearing a tag, the blue color, and again on that there is a white color print. I'm able to see. So that is a resolution. So in similar thing, in electromagnetics, in radars also, when you want very fine details with respect to angle, with respect to the object shape and size, you need to increase your frequency. Okay. Now, space exploration. Yes, when you want to see distance objects and all, also it is used. I'm not much knowledge about, but how they use, try, you can Google and find. So UAVs navigation, drones, when they have to move, several other applications. I have not much highlighted. They are very popular. Can you go next? Ultrasonic, I already mentioned. And today the ultrasonic sensors are heavily used in the drones as well. Okay, because they want to see the distance from the ground. Simplest, simplest altimeter. It's called an altimeter. So it's the simplest technique. Ultrasonic waves reflect and come back, and they will tell, so they can slow down before landing, like that. Also, any nearby object is there, whether it's hitting, all that. Home automation, industrial automation, you see. And I think most of the future smart devices would use radar for your gesture detection. For example, you might have seen some of the latest coming laptops. If you just put it like that, you are not touching the screen. You just say like this, it will go to the next slide, next page. These are all what they use, some kind of radar principles. Okay, go next. Robotics, of course, they need that. Okay, I have not covered other category applications you can study. We'll get into the actual subject basics. Okay, now this is where we will start. Radar can be built basically by, see, I send a pulse and I keep waiting for receiving signal. When I receive a pulse, I measure the time difference, isn't it? And based on that, declare the distance. Okay, and I know what frequency I'm sending. I will measure what frequency I'm receiving. Rather, I will measure the difference of frequency. Okay, then it will tell me the velocity of the target also. We just studied the Doppler effect. The frequency, what I'm sending, F1. The frequency received is F2. If they are same, there is no relative movement. Velocity is 0. If I am also stationary, then velocity is 0. If the frequency has increased, target is coming towards me. That's what we just now learned. So, first, to start with the pulse, what are all the properties of the pulse which you must be conversant with when you are processing, when you are applying that? It is a very simple thing. You must have done, if you guys have done some preparation for GATE and all, then you must have gone these subjects even much deeper. So you will have a pulse, will have a rise time, it will have a fall time, it will have an on time. A practically generated pulse will not have a smooth rising and falling edge if it is generated by some what is it called, circuits which are purely analog control. If it is digital control, you will have a methods to handle those uneven things. You will do compensation in your digital coefficients only, so the smooth pulse comes. So you will have a pulse width and you have PRA, two important words. Pulse width is nothing but the time your energy is on, isn't it? You, in your radar course, you must have done some duty cycle calculations. Duty cycle is nothing but pulses divided by PRA. So just keep all this in your mind. We'll go to next slide and see impacts of this. Yeah, please. Okay, I think I just jumped into the subject. Now, there are few video lectures of few of our previous seminars that I think we did what are key skills for radar, signal processing engineers, right? So please do share the links. So if you have not studied this FFT in depth, maybe you'll find some missing background here. But I'll assume that you studied your Fourier transforms, fast Fourier transform and all. Can we just have quick question answers on this? What is continuous time Fourier transform? Time domain signal to frequency domain signal. What is discrete time Fourier transform? What do you think that you will use in all these products for building? Will you implement continuous time Fourier transform or discrete time Fourier? Discrete time. Why? That is what only possible. Continuous time Fourier transform is impossible. Continuous time Fourier transform is a concept where the ideal equation to understand the conversion from that, it is not implementable. Continuous time, the time is actually infinite precision, it is going there. Okay, discrete time Fourier transform is its modified version which is implementable in your processors, FPGAs and all. So you guys know discrete time Fourier transform. What is fast Fourier transform? Correct. Fast Fourier transform is computationally efficient method to compute your Fourier transform, which is for discrete signals. Are you getting? So FFT is not a very complicated thing, but there are a lot of sources available. So I've given some of them here, but they already assume that you know FFT and they're talking about the windowing functions. Here, I would like to just can you stop screen sharing for a while? Where are we now, Vishnu? I have another 20 minutes at least. Okay, right. So what is it I was referring to? What was the slide? FFT. Okay, right. Now let's go back to again physics. You studied about physics principles and all. Anyone of you understand this concept of called time frequency uncertainty? There is a time frequency uncertainty. In your somewhere when you studied about the physics, Bohr's model and all, there you also have a mention of this, or if you have studied any basic article in quantum theory and all. Correct. What does it mean? Okay, let me put in this way so that easily you'll understand. We are not interested in a deep theoretical physics or that. It's okay if you can read, that's really nice. But in application perspective, to an infinite precision, if you want, or I will say a very small precision you want in frequency, you need an infinite observation in the time. So very detailed information in frequency when you want, you need infinite time observation. And very detailed in the time when you want information, you need infinite frequency processing capable system. So I'll put a couple of examples so that you understand this easily. You take this only as an example, Doppler frequency radar. Okay. Now in radar, I want to measure the velocity of the star. Velocity is nothing but, when you measure the Doppler shift frequency, you can calculate back the velocity. You have the equation, Doppler shift relative velocity and all. When I want to compute to a velocity with the centimeter per second accuracy, meter per second is easy to compute. Centimeter per second, millimeter per second accuracy, micrometer per second accuracy, you would require the frequency measurement also to go to hertz level, millihertz level, microhertz level. When you want that, you would require 1 hour of the processing time of the radar transmitter for that to give. Are you getting a broad understanding? What is this trade-off? Whereas, if I say I'm okay to measure with a 1 meter per second resolution, I'm okay. I don't want, so if the real velocity is 0.9 meter per second, just give 1. 1.1 also you give 1, that is enough. If it is 1.6, you give 2 meter per second. So I am only just interested in at a 1 meter second level resolution. Then the radar can give reading in a millisecond also. Why? You are not demanding very precise information in frequency, right? So if you demand very preciseness in frequency, you need very long time, inversely proportional. Okay. Are you getting my point? So this is why you need to understand this trade-off is, In fact, this is what the crux of the radar system design. When you are designing a radar system, it requires to meet certain functional characteristics. Like for example, you take our company developed products like a drone detection and all. We want that drone velocity also moving, but I'm okay with 1 meter per second. I don't need much high, because anyhow my detection range starts at 4 kilometer, 5 kilometer, 6 kilometer, that range. And 1 meter per second resolution is good enough. Even if it is coming 10 meter per second, 11 meter per second, that's okay for me. I don't have to tell 10.499 meter per second. There is no use, because if I demand that, I would require rather 10 minutes to tell. By the time the drone will come to us, we have to detect early. So the choice of this time frequency trade-off will come in most of the engineering applications design. Okay. And it is not that easy. At a top level, it looks easy, but when you go deeper and try to play with those algorithms and all, you really see that you have hit the bottom. Okay. There is nothing to dig further. That is a physics trade-off. You can't do anything with that. Okay. But you can reinvent some computational tools, like fast Fourier transform is something like which plays fair with time and frequency. Okay. Fair in the sense like time is also uniformly quantized, frequency also uniformly quantized. You guys have done those calculations in your signal processing course in FFT. If you have a signal which is sampled with 1 mega sample per second, then your FS is 1 mega sample per second. In your discrete Fourier transform, which is nothing but same as FFT, the discrete Fourier transform is a basic equation. FFT is a computationally easier way of implementing the discrete Fourier transform. If you are doing 256 point FFT, it will show that your minus 500 kilohertz to plus 500 kilohertz, which is minus fs by 2 plus fs by 2, is quantized uniformly. You got it? Uniformly, in the sense, like, in a scale, you all see that graph book where there is a uniform division is there. Fast Fourier transform plays fair with all the time and frequency. It's a uniform sampling, uniform frequency domain also value. Wavelet transform gives you a method to play with. Okay, you don't want to be uniform in the frequency measurement. So coming back to the main topic, so the time frequency uncertainty is the main challenge, main physics wise limitation you will play with when you are designing any radar system. When you want to, now I will put another general example. You might have seen your oscilloscopes, right? In your oscilloscopes, there is something written on the top of the oscilloscope: 100 megahertz bandwidth, 1 gigahertz bandwidth, and all. If you want to measure, previous slide I was showing the pulse rise time. You want to measure the pulse rise time, let's say, which is order of some microseconds. 100 megahertz bandwidth oscilloscope is enough. You can give that signal. You can zoom into that rising edge. If it is a storage oscilloscope or something, then you can see rising edge and all. When you want to see the rising edge of that pulse at the order of nanoseconds level, okay, I want to go nanosecond precision. What do you need? Would you require a higher bandwidth oscilloscope or lower bandwidth oscilloscope? Higher bandwidth oscilloscope. 100 megahertz won't be enough. You need 1 gigahertz bandwidth oscilloscope, 2 gigahertz bandwidth oscilloscope. This is what the trade-off. When you want to go very finer details in time domain, you require to be broader in the frequency domain. So you should be able to take the, this one, what is called bandwidth 1 gigahertz. Then only you can measure the pulse rising edge very precisely. So this is a very, very important trade-off to be understood in depth, so that everywhere that you see, this fellow comes into picture. Okay. Yeah. Can you put the slides back? Okay. Now, what is this? Go to the previous slide. This is a very important. So as I mentioned, see, what is the purpose of this workshop? One is to enlighten you on the important concepts that you already know and connecting that with the radar. Second is I want to tell practically what gets added on top of what you know. So that's why I picked a topic, very interesting topic. If you master this and go and appear any what is it called, core software development, like signal processing engineer for radar communication, this topic, if you answer all questions, they'll give you 1 lakh per month salary without any doubt. This is a very, very important concept and very deeper concepts. Applying this while designing your algorithm or this is actually what is it called, not that easy thing. It requires a meticulous practicing, learning, reading, calculations, computations and all. Okay. Now what is this? What is this windowing and all? So I'm encouraging you guys to learn this, read this. There is an article reference given beautifully. It is explaining about that. See, what are you doing when you're doing FFT? Just go to the previous example. You have an ADC which is sampling at 1 microsecond. That's why you said sampling rate is 1 microsecond, or the sampling rate is 1 megahertz, or the sample interval is 1 microsecond. So 1 megahertz, that's why you said minus fs by 2 plus fs by 2 minus 500 kilohertz to plus 500 kilohertz. Now this, how much time you need to acquire 256 samples for an ADC which is running with 1 megahertz clock? I'll repeat my question again. You want to compute 256 point for fast Fourier transform. How much time you need for an ADC samples to be acquired? How much time over the time you acquire, which is running with 1 mega sample per second clock? You need 256 point FFT, so you need 256 values, time domain values. How much time it needs? How much time? It's very simple. Could you follow my question? There is an ADC which is clocked at 1 mega sample per second. Okay. You need 256 such samples in your processor to process them for FFT. How much time you take for acquiring the data, acquiring those samples? The clock is 1 mega sample per second, 1 megahertz. So what is complexity in this? Just compute its sampling time, which is 1 microsecond, 256 microseconds. Huh? Yeah, 256 microseconds. So it's good, you give attempt in solving this kind of online calculators and all, they are very handy. So practice all of them. These are very important basics. Okay. So you are taking only 256 microseconds of the time only, right? And you are trying to do the estimation in the frequency domain. So you don't get with very high precision. So what happens? A signal which is supposed to fall in one bin is nothing but in your fast Fourier transform equation, the K. You have that equation, right? X of K is equal to, isn't it? X, that in the time domain to frequency domain, the K is nothing but the bin number. So when you even though you give a sine wave, which is like a simple sine wave, technically it is supposed to come in only one bin. It won't be restricting it to one bin because you took only 256 microseconds, which is, so you want a very high precision frequency exactly to come, you need a more time. You got it? So what happens, even though for one K value, you are supposed to see the peak that actually distributes into the other peaks. I think the next lab exercise is going to have a couple of experiments on this one, the FFT, spectral leakage and all. Are you following? So how do you avoid that? To avoid that, especially on the transitions, because you're cutting the signal, okay, isn't it? Instead of taking the infinite time, you are taking a small chunk. Even that small chunk, you are cutting just like sharp cut, because the remaining all samples are zeros. The remaining all other samples are zeros. From here, I have samples. Now, this becomes a challenge. This is what is your rectangular windowing. Okay. So what we would like to do, instead of cutting that, we would like to apply some windowing functions. Okay. I'm sorry, I did not show the time domain. Here it is there. Yeah. So this is a signal. Whose spectrum, if you'd like to see, I don't have a pointer. Yeah. Do I have a pointer? I just give. This one. There is a switch, I think. It's not visible enough. Okay. So now what you see in the red on top, you notice that there's a leakage that is happening. Even though the frequency is only in the XK, but in the adjacent case also like a ripples you see like this, right? Okay. So this is your, yeah, please, sir. Yeah. So you see like these ripples where the energy is getting leaked. So this is called spectral leakage. Okay. This is called spectral leakage. So see, because what you're doing, you are suddenly truncating here. All these are zeros. All these are zeros in between energy. So because you're suddenly truncating, the energy leaks into this. Whereas if you multiply this with a window function, this is a window function. Okay. This is there in your DSP course. Okay. It's not completely out of the undergraduate syllabus. It is there. So when you multiply window function, the resulting signal is like this. Because you are letting the transition to happen smoother in frequency domain, you will be able to control this leakage. You will be able to minimize the presence of this signal in here. Why this is so important? Why this is important in the products like a radar and all? In radar, let's assume that there is a target which is coming with some velocity, some 100 meter per second, something very high speed target is coming. Now, that target has a stronger energy, stronger echo. What will happen? When you compute its frequency, its energy gets leaked into the other this one, because in Doppler the frequency and the velocity are one and the same, in the sense you measure velocity with by observing the frequency or by measuring the frequency. So the frequency of one target which is supposed to be here will put its energy in the other components also. Imagine there is one more target whose speed is corresponding to this frequency and that has a lesser power. Then this ripples will mask that. You understand? Do you agree or not? So what you would like to do, in not only in radar, in most of the applications where you use FFT, you never use FFT with a rectangular window. Rectangular window means no window. You directly take the samples just as a discrete cut. Okay, you will apply some window function and you'll do it. And now you see, the actual thing is to understand there is a trade-off between two things. There is a trade-off. In engineering, it is always you design with some trade-offs. That's it. Different options you have. Which option you make and depends upon where you can trade the properties of the system. So in this slide, you see the second figure that it is showing. There are two important things you have to observe. The x-axis is nothing but the FFT bin number, and y-axis is nothing but the power that is computed in the dB scale. Now, if you just look at this extreme example, the 7-term Blackman-Harris window function is good that its side lobes are very less. Almost if you compare with the 0, it is less than 150 dB down and all, almost like maybe 160 or 170 dB down with respect to peak. It means, go back to the first figure where that red color figure is showing, the side lobes, you are able to push so low that for me it is possible to detect a very big aircraft and a very small drone. Okay, who are actually moving with almost nearby velocity. For some reason, assume you may say, sir, how drone will move so fast? But let's assume a hypothetical condition, they are moving with same velocity, just adjacent frequencies. I want to detect both of them. Then I need to see that this stronger energy is not masking the other things, right? So that is what is called side lobes. Okay, but you see the challenge is when you want such a very low level side lobes, you would mask a substantial number of bins. You understand? So I give away certain, I mean, like I'm letting my, what is that called, this peak to little broaden, but I'm able to suppress very less. You got it? Whereas you choose another window function, let's say 4-term Blackman-Harris. You are able to see 4-term Blackman-Harris. I'm able to achieve around minus 80 dBm kind of, what is it called, minus 90 or something side lobe level. But it is able to restrict its energy up to only 4th bin. This 4th bin is nothing but your K values that you increase in your FFT equation. It's a trade-off. You want to push all the other bins to very low level. You have to sacrifice more number of your adjacent bins. You see the topmost fellow, which is a no window, is ideally like it is able to hit its 0 in the next bin only. That is what your equation, your fast Fourier transform equation is. The eigen functions in your fast Fourier transform multiplication, xk equation, the x of n into e power minus j omega n is so selected, what you call, kernels. It's called as a kernel, or there is one term used in your signal system. Eigenfunctions. They're called eigenfunctions. They are such that whatever is a correlating eigenfunction at this bin will have nulls, in the sense like they correlate very poor in the adjacent bins. So this fellow, which is the no window, is good that the second bin, which is a bin number 2, I am able to detect, but that will be only 13 dB down. Actually, it is not there because I remember that I'm able to tell you it is 13 dB down with respect to peak, but it will be slowly fading out. Even if you go 10 bins away, this fellow is still not even achieved the 50 dB side lobe. You see this? So this is what a very important thing. Invariably, you have to implement your systems which respond in microseconds, milliseconds, and all, right, isn't it? So whatever the systems that you are going to see today demo, its update rate is 5 seconds radar. So in 5 seconds, you have to scan all 360 degrees and tell all the drones which are coming in all directions. So obviously in one direction, you have to stay in few milliseconds, maybe tens of milliseconds. So invariably you want things to work in faster. Since you are giving a very small time, you have basically frequency domain sacrifice. While doing the frequency domain sacrifice also, if you don't apply window function, you will considerably mask your other targets, adjacent frequencies and all. So the choice of window function becomes extremely important. So I think you have a lab session today afternoon where you are given a pulse Doppler model, one MATLAB model, Octave or MATLAB, any software you can use to run. You change its, what is it called? Now you will be able to see in the range Doppler map that the energy, even though it is at one fixed range, one fixed Doppler is there, in the pulse Doppler map, you don't see only one peak coming. You will see a spread that is coming. Okay. Can you go to next slide? Maybe I can explain there. Okay, I think there is a topic. Let me spend little time on this. This is already you studied in your college days. Okay, signal systems you studied that if you have only one rectangular pulse, let's assume no other pulse, then it is going to be a sink, a continuous time sink. You know that, right? You have only one rectangular pulse and no pulses. It is going to be a sink kind of thing. If you have a periodic signals, then it is a Fourier transform. Sorry, it's a Fourier series. I mean, you will have a discrete spectrum with this one. Even though there is a sink shape that is shown here, that is only shown to show that there is an envelope which is there. But if you just compute its Fourier transform, you will see that only these peaks will be present, these spikes, impulses will be present. Now, as you are trying to make this pulse width whatever narrow, this sink lobe it gets extended. Okay, as the pulse width you want to make it broader, isn't it? In the time domain you make broader, in the frequency domain its bandwidth reduces. The first null sink will keep reducing. As you keep moving these pulses far, you would see that these impulses which are in frequency domain comes closer and closer. Observe this, observe this. This is a short pulse. These two you compare, and the first and third you compare. So the first one you see that you have basically the what is called pulses are separation is this much. The pulses separation is increased. Now you will see that they are coming closer. Okay, you may ask, sir, why you are telling all this? What is the purpose? Why do I do this? Your waveform design is invariably a trade-off between time and frequency domain requirements. Time domain, you make a very narrow pulse, you will be able to detect, okay, with a good range resolution. Because if the pulse is narrow, then only, let's say she is there and next to that one more person is there where distance is only 0.5 meter. If let us say the first target echo is coming, and by the time before its echo gets completed, if the second target echo also gets merged with that, I can't see that there are two targets are there. I'll see it's only one echo, which is a continuation, right? So if I'm able to compress, if you're able to make the pulse smaller and smaller in time domain, I'm going to make a fine, range wise, I'll get a better thing. But when you make pulse smaller and smaller, with respect to this, you see pulse smaller, its bandwidth increases. Isn't it? You may ask, sir, what is the challenge in bandwidth increasing? In digital signal processing implementation, one of the implementation wise challenge, once the bandwidth increases, is straightforward. If the bandwidth is increasing, it means obviously your sampling rate increases. You know Nyquist theorem and all. If your sampling rate increases, your computations need to be faster. If it is a processor-based computation, before the next packet arrives, you have to process this packet and be ready. If it is an FPGA implementation, you would require your FPGA blocks to be clocked at a higher rate, which imposes implementation constraints. And there are other challenges of noises, noise increases. You studied in your noise subject that noise in a system is proportional to the bandwidth, isn't it? KTB. If B, bandwidth of system is higher, the noise is higher. So all those challenges. So when you want to get the advantages in time domain improvements, you have to compromise in frequency. Similarly, when you want to get advantage frequency, and there are a lot of deeper things about the PRA and all, PRA, PRF. So I'll not talk about them. Can you go next? Okay. Now, yeah. So next, what you have to do, let's say for example, a simple thing, a simple philosophy. Acha, so far I've been focusing about only phase, time, frequency, wavelength. I did not talk about one important characteristic of a signal: power, amplitude, isn't it? Having understood that it is simple and you guys can easily visualize, I did not focus much. So the amplitude and power of the signal is very important. And what it matters is not the instantaneous power, it is the average power. And I want you people to intuitively keep this in your mind, at the back of the mind. It is something like, in general, for example, you study for one day very seriously. Does it matter? Rather, you study, it's average efforts that matter. So not only anywhere in the nature, not only in this, it is the average that gets actually created this one, or creates an impact. So you need more average power, okay, more average power for the purpose of detecting the long range targets. And also, when you want a long range, you need to increase the average power. Average power increasing in the sense, the equation of average power. Average power is equal to peak power into duty cycle. Peak power you can increase up to some extent, but beyond some limit you can't increase. Devices burn, heats get generated, a lot of challenges will be there. So what you do, if you don't have an option of increasing the peak, you will increase the pulse width. The average power is equal to peak power into pulse width by PRA. So when your pulse width is higher, the power increases. When your average power increases, your detection capability of a long-term targets increases. In fact, in this context, it is relevant to understand something called radar cross-section and all, but having understood most of your undergraduate background students, so I'm not getting into deeper aspects of that. But if you, if you want to detect longer range things, you need to increase your pulse width, so that average power increases, detectability increases. But increasing the pulse width has got a problem. What? I just now discussed about increase the problem. No, increasing the pulse width will reduce the bandwidth. That's a beauty, actually. Beauty, but it has a problem of range-wise measurements gets compromised. Your range measurements actually goes compromised. Just now we discussed. So your pulse is so long, the first target, second target echoes are merging on each other and coming to me. Here, a new category of the subject comes into picture called pulse compression. So it's a subject in itself. So probably there can be a very detailed workshop on pulse compression techniques for maybe postgraduate students who are already into radar signal processing and all. So pulse compression is a method you still do like this, but improve your range resolution. Okay, your pulse is still broader for your average power detectability chances, but you compress the pulse. So on the air, the pulse is still 10 microseconds and all, but you still compress the pulse. In your processing, you get an advantage. That's a beautiful subject. And its origin is from your correlation chapter. In your DSP, you did that correlation, right? Autocorrelation, cross correlation and all. That's the mother of all these subjects. In fact, if you guys can visualize, your fast Fourier transform is also a correlation. Fast Fourier transform, for one xk, you take xn and correlate with e power minus j omega n by this one, isn't it? That's only a correlation. So entire your signal processing, wherever multiplication is there, there's a correlation only. So study those correlation properties in depth. Okay, yeah, go to next. So I'm not going into pulse compression topic. I'm just telling that's a solution. Still you wider, but achieve the range advantage by compressing the pulse in your processing. Okay. Now we are here. We're just discussing now a basic architecture of a radar. This is a mostly I took a very simplest possible this one, so that you can appreciate and connect with your courses, academic courses and all. You generate a pulse and you upconvert. You studied in these super heterodyne receivers and all, right? In your communication course, up conversion systems, down conversion systems. So you upconvert the signal, okay, and you put it into the air through amplifier and antenna. You have a target. The target actually echo comes. You have either same antenna you switch or separate antenna. Low noise amplifier. You studied about this noise figure and all. Okay, low noise amplifier. Then you have again a down converter. After down converter, you keep low pass filter so that you remove unwanted noise and all, and only restrict that. Then ADC. After that, you have the digital processing. Okay, doing digital processing deeper. Same whatever we discussed now has to be implemented in C programming in a processor, or maybe VHDL, Verilog programming, in FPGA. something, some way it has to be implemented, the digital signal processing in this. Okay. Now, yeah, can you go next? Okay, I'm directly jumping. I'm not getting into the how you implement that. Hopefully, the afternoon lab exercise will give you more deeper understanding. A pulse Doppler radar finally boils down to giving your result, giving your final outcome in a form of basically a range Doppler map. It's called RD map. Okay. What is this range Doppler map? Range Doppler map will show on one scale range, second scale Doppler. The speaker in the second session afternoon will tell how this map gets generated and all before you do the lab session. That time you will go deeper how this gets created. For time being, just understand that this is the outcome of the algorithm. So what you see is, if a target is present, I don't know from where this reference I picked up, maybe this is in meters or kilometers, assume they are meters. So what this fellow is showing that there is a particular target, this kind of target which is presented so on so 14 meters or something, and this target is present somewhere at some 13 meters or something, whereas this scale is showing it's a Doppler bin number. Okay, this is more implementation level, but after computing that bin resolution, in your FFT, what is the resolution in your FFT? The resolution is nothing but, we took that example, right? 1 megahertz, and you did 256 point FFT, then one xk to next xk. Of course, the k is 1 to 256, you will increase 0 to 255. But in the actual frequency terms, what is the separation of 2k adjacent values? It is nothing but 1 megahertz divided by 256. Isn't it? Roughly around 4 kilohertz. Okay. Why that? It is simple. My FFT is invariably minus fs by 2 plus fs by 2, which is minus 500 kilohertz to plus 500 kilohertz, which is equal to 1 megahertz only. I am putting 256, samplings of that. So your discrete Fourier transform is nothing but the sampled of your continuous time Fourier. So you have 256 samples. So separation is nothing but 1 megahertz divided by 256, which is 4 kilohertz. So these things is going to be frequency. So it is telling that this fellow is at a higher velocity than this fellow, this target. They are two separate targets. Following. So finally, a pulse Doppler radar gives you a range Doppler map. In the range Doppler map, you have a peak detected. So now I will put, so y-axis, with this y-axis is nothing but the power. Okay. So I will put some threshold. Anything above that power, I will say it is a target. And I will see at what axis of the range, what axis of the Doppler that is coming to declare what range it is and what velocity it is. Okay. And now next question comes, what direction it is. Direction is not there in the range Doppler map. Direction I will get based on different type of radars. There are different ways to do it. Now what you are going to see when you see the practical radar on the rooftop, that it is actually a rotating type of radar. So rotating type of radar has a principle that it has a very narrow azimuth beam width and it rotates that. Okay, let's say some 6-degree beam width is there, it rotates that. So I'll be able to tell whether in this 6-degree target is there, this 6-degree target, like something like that, I'll be able to tell. Okay. And if you do some digital beam forming with multi-antenna arrays in that, you will be able to tell more precisely within that 6-degree, like that. So the direction when you want to tell, that is not there in the RD map. That is there the time at which this RD map is created. You understand? My servo is rotating, radar is rotating, the beam is here. Now I get an RD map where I have a range of 1 kilometer, velocity of 10 meters per second. So I will tell, because my antenna is looking into some 30 degrees like this. So in the 30 degrees direction, I have a target with velocity of 10 meters per second, range of 1 kilometer. You got it? So this is how you do a 3-dimensional measurement. So this is if a radar is capable of measuring range, azimuth angle, elevation angle, I mean the height of the target, then it is called a 3D radar. You understand the basic 3D concept of a 3D, right? All 3 axis values, range, azimuth angle, and height. If you are able to measure, or using the same range elevation, you can also measure XYZ also. Okay, yeah, go next. Okay, so like a basic signal processing in radar would require an ADC and a pulse compression technique if you want to get the advantage of the average power high, at the same time range is improved, range resolution improved. Then you have to live with the clutter. Clutter is nothing but the stationary ground, which always gives some power, right? It is always there. Ground is always there, because you can't make a very, very, very narrow beam so that I look like this. It's difficult. Got it? So what happens? You have to have some methods. You remove the clutter. One of the easiest, detection of removal of clutter is clutter will not move. Clutter will not move, but the target moves. So in the range Doppler map, where velocity is zero, nearby the zero, why I say nearby? Because spectral leakage is there invariably. You can't limit the zero to exactly zero only. It will little bit spread. So I'll remove the zero and nearby certain small velocities like 1 meter per second, 2 meter per second velocities. Then afterwards, there is no problem of clutter. The energy in the range Doppler map will limit, the clutter energy will limit to only the zero frequency nearby. Okay. Yeah. Then you do what is it called Doppler processing, which is okay. Ambiguity resolution is different. If some of you did the radar course, you know the equation of that radar range ambiguity. Because if I'm sending a pulse and before the echo comes, I'm sending next pulse, I do not know which one it corresponds to, that you studied. It's a very basic thing. So ambiguity processing, then algorithm. There is something called constant false alarm rate algorithm. That is a signal processing technique which adaptively puts your threshold such that your targets are detected with a given false alarm. What is false alarm? There is no target, but you say there is a target. That's a false alarm. What is target miss? There is a target, but you say there is no target. There is a target miss. Again, it's a trade-off. You want to tune your signal processing for the reducing your false alarm. Reducing your false alarms, you will miss sometimes targets, small targets. I want, let us say, to detect all small targets also, slow moving targets also, you give a lot of false alarms. You understand? Because you are going close to the zero Doppler frequency in the range Doppler map, where the clutter leaked energy sometimes may get detected as a Doppler component. Okay. So when you say, sir, it's okay, clutter I don't want, 1 meter per second is also not required, 2 meters also, 5 meter also is not required. Can you give with the low false alarm? Yes, it is possible. Because you are letting all that wherever the clutter leakage, that zone all you are letting down. But let's say, no, I'm interested in 1 meter per second also. Obviously, you have to live with increased false alarm for the same environmental conditions. Got it? Yeah. So there are two things in any particular target radar. There are two things which are called target detection. Detection is only one time. It just comes at 1 kilometer at 10 meter per second. I have a target which is coming towards me. That's only detection. What is tracking? Let's say in rotating radar, I have now detected. I'll go one complete rotation and come back. Now again, that because it's a 10 meter per second, if my rotation is 1 second, it would have moved 10 meter. Now I will get a range of 990 meters. 1000 minus 10, 990. Another 1 second, it will come 980 meters. All these in my algorithm, I'll be connecting these dots and will be able to show in a map with a line, hey, there is something coming like this. This is called a track. Okay. So detecting a target is one thing. Then next one is a tracking is nothing but a long-term observation based information to the user is nothing but a tracking, a long-term observation. Okay, at this time there is a target, at this time there is a target. If you show, that is one thing. Track is nothing but I make multiple measurements and it gives more confidence. Do you agree or not? For example, false alarm is there. Will it come like a track? It won't come, because false alarm is a random phenomena, just comes and goes. But if I am able to see consistently, first 1 kilometer, next rotation 990, next 980, 970, as I keep getting more and more observations, I can say there is a potential threat. There is some drone is coming towards us. Because I don't have one detection, I have multiple detections which are formed as they are logically connecting. Because whatever velocity it is showing, whatever distance it is moving, they are matching. 10 meter per second also I measured. Next time I know 1 second I'm taking, it is matching. So this is called track building. Track building algorithms again is a different subject in radar, and it is a specialized subject application to application. When you are building a track detection building algorithm for drones, quadcopters, they are one type, and for fixed wing they are very other type, because a quadcopter can come like this, like this, like this, it can go, but fixed wing cannot go. Fixed wing has to go like this. If it has to take a bend, it has to take a bend like this. It cannot just like that reverse fixed wing. But quadcopter can go and can go there and just reverse from there. You got it? So track building algorithms are specialized towards the type of the targets. Like missiles are there. Track building algorithm is different. Obviously, an object which is going with a very high speed like a missile, like you must have heard about this BrahMos missile, which is almost supersonic missile, 3 times velocity, 1 kilometer per second it can go. An object which is moving 1 meter per second, 1 kilometer per second can just tilt like this immediately? No. So in your tracking algorithm, you will put all those settings. Got it? Yeah. Okay, go next. Okay, now I'll close with this giving introduction of FMCW. FMCW is not much today we are going to focus on, but this is one of the wider industry, but we are not working in this. So the FMCW, what it does is, it has, okay, first you understand the architecture of FMCW. As the name suggests, it is a frequency modulated continuous wave. So as you can see here, if you can carefully see this small figure, which is it possible for you to put the mouse onto the screen? Actually, I should have done from the beginning, because in the online for online participation. So if you see the pulse, whatever is there, frequency is low, frequency is increasing. Again, low frequency is coming like this. So I am repeating the same frequency modulation, low to high frequency, again low to high frequency, low to high frequency. If I put on x-axis time, y-axis my frequency, I see like a ramps, like kind of ramps, it will be keep coming. Okay. Now, what is the basic principle in it? I send a particular signal and now I receive a signal. Because the frequency I am changing so fast, when I beat in the sense mixing. When you mix your transmitter and the received echo, when you mix them, whatever the difference in frequency will tell the distance, isn't it? See, I'm changing my frequency damn fast. Let's assume that I'm changing every 1 megahertz for 1 microsecond. That's what my sweep rate. Simple calculation will give you more understanding of this. So I'm sweeping my FMCW signal. Its sweep rate is 1 megahertz for 1 microsecond, something like that. What will happen if, let us say, I do not know the range of the target, but I could realize that whatever my transmit signal, whatever my received signal, if I beat both of them, if I mix both of them, I'm getting 1 megahertz. What does it mean? There is an echo which is at 150 meter. We did calculations of why 150 meter and all. Because it is at 150 meter, my received signal is having a frequency of 1 microsecond previous frequency, which is 1 megahertz. That's why when I'm mixing these two, I'm getting 1 megahertz component. So that is the principle of an FMCW. So when it comes to the pulse Doppler to FMCW, what fundamentally changes? In pulse Doppler, it is the time delay between the transmit pulse and received pulses. By measuring that, you get a range. But here there is no time delay because you're not giving any time gap. As the name says, CW, it is always continuous wave is there. But you will change your frequency so fast such that the received echo would have definitely a small frequency variation, which I will measure and tell based on the frequency difference, I will tell the range of the target. That's only the difference between a pulse Doppler radar and FMCW radar. And what will be the next point once you measure the range? Next one is you have to measure the velocity. Velocity will be invariably same. It is a Doppler shift here also and there also. It is invariably the same. Okay. Then yeah, these are the basic notes. And there is a very interesting blog given here. Okay. I believe he is like Texas Instruments background engineer, has given some 4 or 5 video lectures, and they are available at this blog, and they are very, very beautifully explained the FMCW radar. So people more interested deeper, you can read. So look at this figure. It explains. See, there is some amount of range. This is the range. This is what the frequency of the instantaneous frequency, I should say. Instantaneous because whenever something is on time x-axis, it is called instantaneous. So instantaneous frequency of received signal is this. So at any instant of time in my mixer, when I am mixing the transmit, so I take a copy of the transmit waveform here, then I will actually mix it here. So the difference, whatever is the y-axis difference you see, this is nothing but my difference in the frequency which comes out of the mixer. So I pass that mixer output through amplifier ADC and then use it, FFT to compute the frequency. Now my FFT is giving range first. Okay. So range it is giving. So it tells the range. Yeah, go next. Okay, so this is again more deeper aspects of mixer and this one. So I would skip this slide as we have less time. And he also talk about the frequency, not only the frequency change, the phase change between the transmit and receive will tell you more detailed information about it. Go next. So when there are multiple reflections are there, you have multiple echoes coming up. You see, this is a copy of the, what is this? This is the instantaneous frequency of the TX waveform. These are the instantaneous frequencies of the multiple echoes which are coming in. So when these multiple echoes, we mix with them at any instant of time, this difference of the transmit to receive of the first echo is one frequency. And here to here, there is a second frequency. Here to here is a third frequency. So if you put x-axis time and y-axis frequencies, you see it's the frequency that changes. So using your fast Fourier transform, if you find FFT in your processor or FPGA, you see like this. You see three peaks. Three peaks corresponds to three targets. And the frequency value will tell the range of the target. Are you getting? Intuitive, right? It's intuitively you should be able to understand the FMCW. Okay, go next. Yeah, this is a common principles of your signal, what is called sampling theorem and all. But what is to be understood, you will not, you are digitizing only corresponding to the difference. So here, this can be very important exercise. If you want to benchmark yourselves that I have understood the FMCW radar, challenge yourselves and solve some problems online or some articles what are available. Having given the sweep rate is what I just took as an example, 1 megahertz for 1 microsecond is a sweep rate. Having given sweep rate, having given the maximum range of the target, you should be able to tell what is your highest frequency of interest that you should be able to digitize for your processing, isn't it? Sweep rate is deciding. For example, I just now took example of 1 megahertz for 1 microsecond. So what happened? A target which is at 150 meter has reported as at 1 megahertz in my FFT, right? Obviously, a target at 300 meter will report at 2 megahertz in my FFT. But if my sweep rate, instead of 1 megahertz for 1 microsecond, if it has become 2 megahertz for 1 microsecond, okay, then what will happen? The same 150 meter target will be detected at 2 megahertz, because by the time the to and fro distance and the time taken by electromagnetic signal, that is not changed. A target which is at 150 meter, the to and fro delay is 1 microsecond. 150 meter up, 150 meter down. So it takes 1 microsecond for the round trip delay. The time is fixed. But if my sweep rate is 1 megahertz for 1 microsecond, then when I'm beating these two for 150 meter, I'm seeing 1 megahertz difference. If my sweep rate is 2 megahertz for 1 microsecond, then same 150 meter I will see at this. Now you see, this is what basically the trade-off again here also. I want very good range resolution. My sweep rate need to be very good, isn't it? If I'm sweeping rate is very fast, then even close targets I can distinguish. Close targets I can distinguish because in my frequency domain they are going far apart. You got it? But whereas by doing, what is the challenge? My sweep rate I want to be damn faster. Then what is the challenge? The challenge is basically the bandwidth increases. Okay, bandwidth increases. So again, so if in any subject you keep a thumb rule for yourselves, in any subject, without getting into equations, qualitatively, if you are able to explain the trade-offs, like increasing this, how it reduces, giving this, how it reduces, means you have understood that subject intuitively. That is most important than the mathematics. Mathematics, if you forget, you can read internet article and do it. But intuitive understanding you missed. Equations will be in front of you, but which equation is implying what, you don't understand. You got it? Same thing will happen when you are working on an actual system. Okay, all results will be in front of you, but you won't be able to connect what is what, why this is coming like this. So intuitive understanding challenging is very simple. Are you able to talk about all trade-offs in the system? Like in a radar, I mentioned about the trade-off of the bandwidth versus the range resolution. So can you tell that? Can you understand that intuitive? That's a question. Okay, go next. Now this is little same thing is being summarized. I just picked this slide. It is there in the video lecture at the end. So for you to recap and understand certain things in this, I'll skip. Having understood, you are new to radar. Okay, go next. I've done. Now let's have quick question answers now. Any doubts? Most of the basics that I discussed now, the sampling, FFT, windowing, certain things connected with the to and fro range delays and other things and all, you will be doing in the first lab session now.